In a laboratory in Germany in 1927, a young physicist made a discovery that would shatter humanity's most fundamental assumptions about reality itself. Werner Heisenberg wasn't trying to destroy our understanding of existence. He was simply trying to measure an electron, but what he found changed everything we thought we knew about the nature of knowledge, certainty, and the very fabric of the universe. Picture this moment. You're holding a flashlight in a completely dark room, trying to find a soap bubble floating in the air. The instant your light touches that bubble, the photons slam into it and send it spinning away. You can see where it was, but now you have no idea where it's going. You can measure its position, but the very act of measurement has destroyed any possibility of knowing its momentum. This isn't just an experimental limitation. This is the fundamental structure of reality revealing itself. Heisenberg called it the uncertainty principle, and it doesn't just apply to soap bubbles or electrons. It applies to everything. Every atom in your body, every particle in the universe, every piece of matter and energy that has ever existed operates under this impossible rule. The more precisely you know where something is, the less you can know about where it's going. The more you understand its momentum, the more its position becomes a complete mystery. But here's what will blow your mind. This isn't about our measuring instruments being imperfect. This isn't about technology that needs to improve. The uncertainty principle reveals that reality itself, at its deepest level, refuses to be pinned down. Nature has built indeterminacy into the very foundation of existence. Tonight, we're diving into the most mind-bending discovery in the history of science. We'll explore how Heisenberg's breakthrough demolished the clockwork universe that scientists had believed in for centuries. We'll uncover why this principle means that complete knowledge of anything is not just practically impossible, but theoretically forbidden by the laws of physics themselves. And we'll discover how this quantum weirdness connects to everything from the existence of atoms to the possibility of free will. By the end of this journey, you'll understand why Nobel Prize winner Niels Bohr said that anyone who isn't shocked by quantum mechanics hasn't understood it, because what we're about to explore doesn't just change how we think about physics, it changes how we think about thinking itself. Before we launch into this cosmic mystery, hit that like button and subscribe, because this journey will challenge everything you thought you knew about the nature of existence. Now, prepare yourselves, we begin. Let me show you exactly how revolutionary this discovery really was. For over 200 years, science operated under a beautiful, simple assumption. If you could measure everything about a system perfectly, you could predict its future with absolute certainty. This was the dream of classical physics, the vision of a universe that operated like the most precise clockwork imaginable. Isaac Newton had given us the mathematical tools to describe motion with incredible accuracy. His equations could predict the orbits of planets, the flight of cannonballs, the swing of pendulums. Pierre-Simon Laplace took this idea to its logical extreme in 1814 when he proposed his famous demon. Imagine an intelligence that could know the precise location and momentum of every atom in the universe. This demon could use the laws of physics to calculate the entire future and reconstruct the complete past. Nothing would be uncertain. Everything would be determined. This wasn't just theoretical speculation. Classical physics had delivered miraculous practical results. Engineers built bridges that stood for centuries. Astronomers predicted eclipses decades in advance. The Industrial Revolution was powered by mathematical certainty about how forces, energy, and motion worked in the real world. Then came quantum mechanics, and everything fell apart. The trouble started in the early 1900s, when scientists began studying the behavior of atoms and subatomic particles. The classical equations that worked perfectly for baseballs and planets produced completely wrong answers when applied to electrons and photons. Strange phenomena kept appearing that seemed to violate the fundamental assumptions of physics. Light sometimes behaved like a wave, creating interference patterns just like ripples on a pond, but other experiments showed that light came in discrete packets of energy called photons, behaving more like tiny bullets. Electrons exhibited the same schizophrenic behavior, acting like particles in some experiments and waves in others. Even weirder, the act of observation seemed to affect the results. When scientists tried to measure which path an electron took through a double-slit experiment, the electron would behave like a particle, but when they weren't looking, it would behave like a wave and somehow pass through both slits simultaneously. This was the scientific crisis that Heisenberg walked into as a young researcher working with Niels Bohr in Copenhagen. Traditional physics assumed that particles had definite properties whether you measured them or not. A baseball has a specific location and velocity even when nobody's watching it. But quantum particles seem to exist in a strange limbo where their properties remained undefined until someone tried to measure them. Heisenberg's breakthrough came from taking this weirdness seriously instead of trying to explain it away. He developed a new mathematical framework called matrix mechanics that could accurately predict the behavior of quantum systems. But this mathematics came with a shocking philosophical cost. The equations revealed that certain pairs of properties, like position and momentum, could never be measured simultaneously with perfect accuracy. This wasn't a limitation of experimental technique. It was built into the mathematical structure of reality itself. The universe had a fundamental graininess, an irreducible fuzziness that no amount of technological advancement could overcome. Think about what this means for our understanding of knowledge itself. Since ancient Greece, philosophers had debated whether true knowledge was possible, but they always assumed that if perfect knowledge existed, it would involve knowing everything about everything with complete precision. Heisenberg showed that this kind of perfect knowledge is not just difficult or impractical, it's forbidden by the laws of physics. The uncertainty principle comes in several forms, but the most famous involves position and momentum. The mathematical relationship is elegantly simple but philosophically devastating. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to Planck's constant divided by 4 pi. Planck's constant is incredibly tiny, about 6.6 times 10 to the negative 34th power joule seconds. This is why we don't notice quantum uncertainty in everyday life. For objects large enough to see with the naked eye, the uncertainty is so small it might as well be zero. But for particles the size of atoms or smaller, this fundamental limit becomes the dominant factor governing their behavior. Here's where it gets truly mind-bending. The uncertainty principle doesn't just say that we can't know both position and momentum precisely. It says that particles don't have definite position and momentum simultaneously. Before measurement, an electron doesn't exist at a specific location with a specific velocity. It exists in what physicists call a superposition of all possible positions and velocities weighted by quantum mechanical probabilities. This isn't just semantic wordplay. Experiments have confirmed over and over again that quantum particles really do exist in these bizarre superposition states until the moment they're observed. The famous Schrödinger's cat thought experiment was designed to illustrate how absurd this seems when applied to larger objects. In the quantum world, the cat really would be both alive and dead simultaneously until someone opened the box to check. But Heisenberg's principle extends far beyond position and momentum. It applies to energy and time, creating another fundamental limit on knowledge. You cannot measure the energy of a quantum system with perfect precision without taking infinite time to do it. This has profound implications for the nature of physical processes and the structure of atoms themselves. The uncertainty principle actually explains why atoms exist at all. In classical physics, electrons orbiting an atomic nucleus should spiral inward and crash within a tiny fraction of a second, radiating away their energy as electromagnetic waves. But quantum uncertainty prevents this collapse. The electron cannot have zero momentum while also being precisely located at the nucleus. The uncertainty principle creates a kind of quantum pressure that keeps electrons from falling into the nucleus, making stable atoms possible. This same principle governs nuclear reactions, stellar fusion, and the behavior of materials at the molecular level. Without quantum uncertainty, matter as we know it couldn't exist. The solid chair you're sitting on, the air you're breathing, the neurons firing in your brain as you process these words, all of it depends on the fundamental impossibility of perfect knowledge. Even more strangely, the uncertainty principle means that empty space isn't actually empty. The vacuum of space itself is filled with quantum fluctuations, virtual particles popping in and out of existence on timescales so brief that energy conservation can be temporarily violated without detection. These vacuum fluctuations have measurable effects on atomic spectra and play crucial roles in advanced theories of particle physics and cosmology. The implications ripple outward into every corner of physics and philosophy. If complete knowledge is impossible even in principle, what does this mean for scientific theories that claim to describe ultimate reality? How can we make sense of a universe where the very act of observation changes what we're trying to observe? Some physicists have tried to preserve classical intuitions by proposing hidden variable theories. Maybe particles do have definite properties at all times, but there are hidden variables we can't access that determine the outcomes of quantum measurements. John Bell proved in the 1960s that any such hidden variable theory would have to allow for instantaneous action at a distance, violating Einstein's special relativity. Experiments have consistently confirmed Bell's predictions, ruling out local hidden variable explanations for quantum behavior. Others have embraced the weirdness completely, proposing interpretations like the many worlds hypothesis, where every quantum measurement splits the universe into parallel realities corresponding to all possible outcomes. In this view, Schrödinger's cat really is both alive and dead, just in different branches of a constantly splitting multiverse. But perhaps the most profound implication of Heisenberg's discovery is what it reveals about the relationship between mind and reality. Classical physics assumed that the universe existed independently of observation, following deterministic laws that we could discover through careful measurement. Quantum mechanics suggests that observation plays a fundamental role in determining what becomes real. This doesn't necessarily mean that consciousness creates reality in some mystical sense. But it does mean that the sharp boundary between observer and observed that classical physics took for granted becomes blurred at the quantum level. Information, measurement, and knowledge become physical processes that cannot be separated from the systems they're trying to describe. The uncertainty principle forces us to confront uncomfortable questions about the nature of scientific knowledge itself. If perfect measurement is impossible, how can we ever be completely certain about our theories? If observation changes reality, how can we claim to discover objective truths about the world? These aren't just abstract philosophical puzzles. They have practical implications for every technology that depends on quantum mechanics, which increasingly means every technology period. Computer chips rely on quantum tunneling. Lasers exploit quantum coherence. Medical imaging techniques like MRI depend on quantum spin properties. The GPS satellites overhead use atomic clocks that account for quantum effects. Even more unsettling, Heisenberg's principle suggests that the future itself might be fundamentally unknowable, not because of practical limitations, but because the future doesn't exist in any definite form until quantum measurements collapse possibilities into actualities. This strikes at the heart of human intuition about causation and prediction. Consider what happens when you try to predict the exact moment a radioactive atom will decay. Classical physics would say that if you knew everything about the atom's internal state, you could calculate precisely when it would emit radiation. But quantum mechanics reveals that radioactive decay is genuinely random, governed only by probabilities. You can know the half-life of a radioactive isotope with incredible precision, but you cannot predict when any individual atom will decay, no matter how much information you gather. This randomness isn't hiding some deeper deterministic process. It's built into the fabric of reality itself. Einstein famously objected to this aspect of quantum mechanics, declaring that God does not play dice with the universe. But experiments have repeatedly confirmed that nature really does include irreducible randomness at its foundations. The philosophical implications become even more staggering when you realize that this quantum uncertainty might be connected to consciousness and free will. If the brain operates as a classical system, then every thought you think and every decision you make would be completely determined by the prior states of all the atoms in your head. You would be nothing more than a biological machine executing a program written by the laws of physics. But if quantum effects play a role in neural processes, then there might be genuine openings in the causal chain where consciousness could influence physical events. Some researchers have proposed that microtubules in brain cells might maintain quantum coherence long enough for uncertainty effects to influence neural firing patterns. This remains highly speculative, but it illustrates how Heisenberg's discovery opens up conceptual space for human agency in ways that classical physics never could. The uncertainty principle also reveals something profound about the nature of information itself. In classical physics, you could imagine copying all the information about a system perfectly without disturbing it, but quantum mechanics shows that information and physical reality are more intimately connected than anyone had imagined. The no-cloning theorem proves that you cannot create identical copies of arbitrary quantum states. This isn't just a technical limitation. It's a fundamental constraint that protects the consistency of quantum mechanics. If you could clone quantum states perfectly, you could violate the uncertainty principle by making multiple copies and measuring different properties of each copy. This has led to an entire field of quantum information theory that treats information as a physical quantity with properties as real as mass or electric charge. Quantum entanglement allows particles to share information instantaneously across vast distances, creating correlations that Einstein called spooky action at a distance. These entangled systems exist in combined quantum states, where measuring one particle instantly determines the state of its partner, regardless of how far apart they are. The implications extend to the nature of space and time themselves. Some theories suggest that space-time might emerge from more fundamental quantum informational processes. In this view, the geometry of space and the flow of time arise from the way quantum information is processed and shared between different regions of reality. Recent experiments in quantum teleportation have demonstrated that you can transfer the complete quantum state of a particle from one location to another without the particle itself traveling through the intervening space. The original particle is destroyed in the process, while its quantum information reappears elsewhere, reconstructing an identical particle from the quantum vacuum. This isn't science fiction teleportation where objects dematerialize and rematerialize intact. But it does show that the boundary between information and physical reality is far more fluid than classical physics suggested. In quantum mechanics, what something is and what we can know about it become inseparable questions. The uncertainty principle has also revolutionized our understanding of measurement itself. In classical physics, measurement was supposed to be a passive process that revealed pre-existing properties without changing them. You could measure the temperature of water without affecting its temperature or determine the position of a planet without altering its orbit. But quantum measurement is fundamentally active. Every quantum measurement requires an interaction between the quantum system and a measuring device. This interaction necessarily disturbs the system in unpredictable ways, changing its future evolution. The measuring device itself becomes quantum mechanically entangled with the system being measured, creating correlations that cannot be separated. This leads to what physicists call the measurement problem. At what point in the measurement process does a quantum superposition collapse into a definite classical outcome? When a quantum particle hits a detector, the detector itself is made of quantum particles that should also exist in superposition states. So when exactly does the quantum weirdness stop and classical reality begin? Different interpretations of quantum mechanics propose different answers to this question, but none are completely satisfying. The Copenhagen interpretation says that measurement collapse is simply a fundamental postulate that cannot be reduced to more basic principles. The many worlds interpretation claims that collapse never actually happens, and all possible measurement outcomes occur in parallel universes. Objective collapse theories propose that quantum states spontaneously collapse when systems become sufficiently large or complex. But perhaps the deepest mystery is why the uncertainty principle takes the specific mathematical form that it does. Planck's constant appears in the uncertainty relations as a fundamental limit, but we have no deep understanding of why this constant has the value it does, or why these particular pairs of properties are complementary. If Planck's constant were much larger, quantum uncertainty would dominate even at macroscopic scales, making classical physics impossible. If it were much smaller, quantum effects would be negligible, and the universe would behave more like the clockwork system that Newton envisioned. The actual value seems to be precisely tuned to allow both quantum and classical physics to play important roles in the structure of reality. This fine-tuning raises profound questions about the relationship between mathematics and physics. Why should the universe be governed by mathematical laws at all? And why should these laws have the specific forms that make complex structures like atoms, molecules, and living organisms possible? The uncertainty principle has also opened up entirely new technological possibilities that classical physics could never have imagined. Quantum cryptography uses the fundamental impossibility of perfectly copying quantum states to create communication channels that are provably secure against any possible eavesdropping. Quantum computing exploits superposition and entanglement to perform certain calculations exponentially faster than any classical computer could. These technologies don't just apply quantum mechanics. They depend on the specific features that make quantum mechanics so counterintuitive. Quantum computers work precisely because quantum states can exist in superpositions that allow them to explore multiple computational paths simultaneously. Quantum cryptography is secure precisely because any attempt to intercept quantum information necessarily disturbs it in detectable ways. But even as we learn to exploit quantum uncertainty technologically, its philosophical implications continue to challenge our most basic assumptions about knowledge and reality. If the universe itself places fundamental limits on what can be known, what does this mean for human aspirations to understand everything? Some have suggested that the uncertainty principle points toward a kind of cosmic humility. Perhaps the universe is structured in such a way that complete knowledge is impossible not as a bug, but as a feature. Maybe the fundamental mystery built into quantum mechanics serves some deeper purpose in the structure of reality. Others argue that quantum uncertainty might be connected to the existence of consciousness itself. If the universe were completely deterministic and knowable, perhaps there would be no room for genuine creativity, novelty, or subjective experience. The irreducible randomness of quantum mechanics might be what allows for the emergence of minds capable of contemplating the universe in the first place. These speculations remain far beyond what current physics can definitively establish, but they illustrate how Heisenberg's seemingly technical discovery about measurement precision has opened up questions that reach to the very foundations of existence itself. The uncertainty principle doesn't just tell us that we cannot know everything, it tells us that the very concept of everything might be meaningless when applied to the structure of reality. In a quantum universe, knowledge and ignorance, being and non-being, possibility and actuality become fluid categories that cannot be separated as cleanly as classical thinking assumed. This represents a fundamental shift in human understanding comparable to the Copernican revolution or Darwin's theory of evolution. We are not just learning new facts about the world. We are discovering that our most basic conceptual frameworks for understanding knowledge, causation, and existence itself need to be rebuilt from the ground up. The journey into quantum uncertainty reveals that reality is stranger, more mysterious, and more wonderful than our ancestors could have imagined, and we've only just begun to explore the implications of living in a universe where the impossible has become inevitable. What makes Heisenberg's discovery even more unsettling is how it reveals the active role that consciousness plays in shaping reality itself. This isn't some mystical claim about the power of positive thinking. This is hardcore physics backed by decades of experimental evidence that should terrify anyone who believes in an objective world that exists independent of observation. The delayed choice quantum eraser experiments demonstrate something that seems to violate our most basic intuitions about time and causation. Scientists can set up an experiment where they decide whether to measure a photon's path after it has already hit a detector screen. Incredibly, this future decision retroactively determines whether the photon behaved as a wave or particle during its entire journey through the apparatus. Think about what this means. The photon somehow knows about measurement decisions that haven't been made yet. The future choice of the observer reaches backward in time to influence events that have already occurred. This isn't science fiction speculation. These experiments have been performed thousands of times with identical results that confirm quantum mechanics while shattering our assumptions about the flow of time. But the strangeness goes even deeper when you consider what happens during the transition from quantum to classical behavior. Individual quantum particles exist in superposition states where they can be in multiple places simultaneously. Yet somehow, collections of these particles create the solid, definite classical world we experience every day. The process by which quantum superpositions collapse into classical reality remains one of the deepest mysteries in physics. Decoherence theory suggests that interactions with the environment cause quantum states to lose their coherence rapidly, making superpositions effectively impossible to maintain in warm, noisy systems like biological organisms. Yet recent discoveries have found quantum coherence persisting in biological systems at room temperature for much longer than theory predicted. Photosynthesis in plants appears to use quantum superposition to explore multiple energy pathways simultaneously, choosing the most efficient route for transferring light energy to chemical energy. Some researchers have found evidence of quantum effects in bird navigation, enzyme catalysis, and possibly even neural microtubules in the brain. If quantum uncertainty does play a role in consciousness, it would mean that your thoughts right now are literally unpredictable, even in principle. No amount of information about your brain state could allow perfect prediction of your next thought. This creates genuine openings in the causal chain where free will might operate through quantum indeterminacy. The implications become even more profound when you consider the role of information in quantum mechanics. John Wheeler, one of the most influential physicists of the 20th century, proposed that reality might be fundamentally informational rather than material. His it-from-bit hypothesis suggests that all physical entities are information-based, arising from binary choices made during quantum measurements. In Wheeler's vision, the universe doesn't consist of particles and forces. Instead, it consists of answers to yes or no questions posed by measurement processes. Every quantum measurement extracts one bit of information from the quantum vacuum, crystallizing a definite classical outcome from the sea of quantum possibilities. This informational view of reality helps explain some of the most puzzling aspects of quantum mechanics. Why can't quantum information be copied perfectly? Because copying would allow multiple measurements of the same quantum system, violating the uncertainty principle. Why does quantum entanglement create instantaneous correlations across vast distances? Because entangled particles share the same informational identity, making them aspects of a single quantum entity rather than separate objects. The Quantum Zeno effect provides another mind-bending example of how observation shapes reality. If you measure a quantum system continuously, you can actually prevent it from evolving. Frequent measurements freeze the system in its current state, like a watched pot that never boils because the watching itself prevents the boiling. This effect has been demonstrated experimentally with radioactive atoms that refuse to decay when observed frequently enough. The very act of checking whether decay has occurred prevents the decay from happening. Reality becomes malleable under the gaze of consciousness in ways that classical physics never imagined possible. But perhaps the most disturbing implication of quantum uncertainty is what it reveals about the nature of scientific knowledge itself. Every measurement we make, every observation we record, every data point we collect is fundamentally limited by the uncertainty principle. We can never escape the observer effect that makes us active participants in creating the reality we're trying to understand. This doesn't mean that science is impossible or that objective knowledge is a complete illusion, but it does mean that the sharp separation between subject and object, observer and observed, knower and known that classical science took for granted cannot be maintained at the quantum level. The bootstrap theory of particle physics takes this participatory universe idea to its logical extreme. Instead of assuming that fundamental particles have intrinsic properties, bootstrap theory proposes that particles are defined entirely by their interactions with other particles. There are no fundamental building blocks, only patterns of relationships that maintain themselves through mutual consistency. In this view, electrons don't exist as little balls with definite properties. Instead, electron is a name we give to a particular pattern of quantum field interactions that maintains its identity through time. The electron creates itself through its own self-consistent interactions, pulling itself up by its own bootstraps in an endless loop of self-reference. Recent developments in quantum field theory have provided mathematical frameworks for understanding how such self-creating systems might work. The ADS/CFT correspondence suggests that entire universes with different numbers of spatial dimensions might be equivalent descriptions of the same underlying reality. What appears to be a three-dimensional world with gravity might actually be a hologram projected from information encoded on a two-dimensional boundary. These holographic theories imply that the familiar three-dimensional space we inhabit might be an emergent property of more fundamental quantum informational processes. Space itself becomes a kind of user interface that helps conscious observers navigate underlying quantum realities that are far stranger than our evolved intuitions can grasp. The anthropic principle adds another layer of mystery to quantum uncertainty. The fundamental constants of physics, including Planck's constant that determines the strength of quantum effects, appear to be fine-tuned with incredible precision to allow for the existence of complex structures like atoms, stars, planets, and living organisms. If Planck's constant were even slightly different, the universe would be radically altered in ways that would make life impossible, too large, and quantum uncertainty would prevent the formation of stable chemical bonds, too small, and atoms would collapse into their nuclei. The actual value seems to be precisely calibrated to create a universe where both quantum and classical physics play essential roles. Some theorists propose that this fine-tuning results from the existence of multiple universes with different physical constants. In this multiverse scenario, we observe a life-friendly universe simply because we couldn't exist in the countless sterile universes where the constants have different values. But others suggest that the fine-tuning might be connected to the role of consciousness in quantum mechanics. Perhaps the physical constants are determined by the requirement that conscious observers must eventually evolve to collapse quantum superpositions into definite classical states. In this view, the universe is structured in such a way that it inevitably gives rise to the very minds needed to make it real through observation. The quantum vacuum itself turns out to be far from empty. Heisenberg's uncertainty principle requires that energy and time cannot both be precisely zero, meaning that even empty space must be filled with quantum fluctuations. Virtual particles constantly pop in and out of existence on timescales so brief that they normally cannot be detected directly. Yet these vacuum fluctuations have measurable effects on atomic energy levels, creating tiny shifts in spectral lines called the Lamb shift. They also generate the Casimir effect, where two parallel metal plates in vacuum experience an attractive force created by the quantum fluctuations between them. Some theories suggest that these vacuum fluctuations might be responsible for the accelerating expansion of the universe itself. Dark energy, the mysterious force driving cosmic acceleration, might arise from the quantum uncertainty of empty space. If true, this would mean that the large-scale structure and fate of the entire universe is determined by the same quantum uncertainty that governs individual particle interactions. The connection between quantum mechanics and consciousness remains one of the most controversial and fascinating frontiers in physics. While most physicists remain skeptical that quantum effects play significant roles in brain function, the mathematical parallels between quantum mechanics and theories of consciousness are too striking to ignore completely. Both quantum systems and conscious experiences seem to involve irreducible wholes that cannot be understood by analyzing their parts in isolation. Both exhibit aspects of complementarity where different types of observations reveal incompatible but equally valid perspectives. Both seem to require active participation by observers to determine what becomes real. Recent experiments with quantum-scale magnetometers have detected quantum coherence in certain biological systems at room temperature, suggesting that evolution might have found ways to exploit quantum effects for computational advantages. If brains do use quantum processes, then consciousness itself might be subject to fundamental uncertainty principles that make thoughts partially unpredictable even to the thinker. The implications extend far beyond individual minds to the nature of knowledge and communication itself. If consciousness involves quantum processes, then the contents of minds might be subject to no-cloning theorems that prevent perfect copying of mental states. This could provide a physical basis for the privacy of subjective experience and the irreducible individuality of conscious beings. Quantum uncertainty also reveals deep connections between information, energy, and computation. Every irreversible computational process requires energy dissipation, creating heat that represents lost information. The theoretical minimum energy cost for erasing one bit of information is determined by Boltzmann's constant and temperature, connecting thermodynamics directly to information theory. This has led to proposals that the universe itself might be understood as a vast quantum computer, with physical processes corresponding to computational operations on quantum information. In this computational view of physics, the laws of nature become algorithms, and the evolution of the universe becomes the execution of a cosmic program written in the language of quantum mechanics. But who or what is running this cosmic computation? Some theories suggest that the universe is self-computing, using emerges from the collective its own quantum processes to calculate co-creators of the physical world, rather its own future evolution. Others propose that reality computational activities of all than passive recipients of scene's conscious observers, making mind-sorry data. The recursive loops where the act of observation nature of quantum measurement creates strange changes the observer as well as the observed. Every quantum measurement entangles the measuring device with the system being measured, creating correlations that cannot be undone. Over time, these measurement interactions shape the evolution of both conscious observers and the reality they inhabit. This suggests that the boundary between mind and world is not fixed, but constantly negotiated through ongoing interactions. Consciousness doesn't simply observe reality from the outside. It participates in creating reality through the very process of observation, while simultaneously being shaped by the reality it helps create. The uncertainty principle thus becomes more than a technical constraint on measurement precision. It becomes a window into the participatory nature of existence itself, revealing a universe where knowledge, consciousness, and reality are woven together in patterns too complex and beautiful for classical physics to describe. We find ourselves in a cosmos where the deepest truths cannot be separated from the minds seeking to understand them. The observer and the observed dance together in an eternal quantum waltz, creating the very reality they explore through their interaction. In such a universe, uncertainty isn't a limitation to be overcome. It's the creative principle that makes existence possible in the first place. This participatory dance between mind and reality leads us to one of the most shocking discoveries about quantum uncertainty. It doesn't just govern the behavior of tiny shapes, the very structure particles in laboratory experiments. It of space and time themselves in ways that would have been unimaginable to physicists just a century ago. Consider what happens when you try to measure distances at the smallest possible scales. Classical physics assumed that space was smooth and continuous, infinitely divisible like a mathematical line, but quantum uncertainty reveals that space itself has a granular structure at distances approaching the Planck length, roughly 10 to the negative 35 meters. At scales, these impossibly tiny uncertainty principle creates violent fluctuations in the geometry of space-time itself. Virtual particle pairs pop in and out of existence so rapidly and with such energy that they literally bend space around them. The smooth fabric of space-time that Einstein described becomes a seething foam of quantum activity, with the very coordinates of space and time becoming uncertain. This quantum foam means that if you could somehow zoom in far enough, solid matter would dissolve into a bubbling chaos of probability waves. The chair you're sitting on right now appears solid only because you're observing it at scales much larger than the Planck length. At the deepest level of reality, that chair is a statistical approximation emerging from quantum uncertainties that extend all the way down to the structure of space itself. But here's where it gets truly mind-bending. Time itself becomes uncertain at quantum scales. The uncertainty principle relating energy and time means that high-energy quantum events can occur for brief periods without violating conservation of energy, as long as they happen quickly enough that the universe's accounting system cannot. Uncertainty allows for phenomena detect the violation. This temporal that seem to violate causality itself. Virtual particles can travel faster than light because they exist for such short times that relativistic constraints don't have time to apply. Quantum tunneling allows particles to pass through energy barriers that should be completely impenetrable, as if they briefly borrow the energy needed to climb over the barrier before paying it back. These quantum violations of classical physics aren't just theoretical curiosities. They power the nuclear fusion reactions in the sun's core. Without quantum tunneling, protons wouldn't have enough energy to overcome their electrical repulsion and fuse together. The sun would never ignite and life on Earth would be impossible. The uncertainty principle literally keeps the lights on in our solar system. Even more remarkably, these same quantum effects might explain the origin of the universe itself. In the quantum vacuum, energy fluctuations can theoretically create particle pairs from nothing as long as they annihilate quickly enough to avoid detection. But what if, in the earliest moments after the Big Bang, one of these fluctuations became permanent instead of disappearing? Some cosmological theories propose that the entire universe began as a quantum fluctuation that grew large enough to become self-sustaining. In this view, everything that exists, including space and time themselves, emerged from the quantum uncertainty of nothingness. The universe didn't come from somewhere else. It came from the inherent instability of perfect emptiness. This quantum creation scenario helps solve some of the deepest puzzles in cosmology. Why does the universe contain matter instead of antimatter? Quantum fluctuations naturally create slight imbalances that could account for the matter-antimatter asymmetry we observe. Why is the cosmic microwave background radiation so remarkably uniform? Quantum fluctuations, stretched to cosmic scales during inflation, would create exactly the tiny variations we measure. But quantum uncertainty also creates what might be the most disturbing implication for human knowledge. Not only can we never know everything about the present state of any system, we can never even define what we mean by the present moment itself. Einstein's relativity already showed us that simultaneity is relative. Events that appear simultaneous to one observer happen at different times for observers in relative motion, but quantum mechanics adds another layer of temporal to have definite moments of confusion. The uncertainty principle means that quantum events don't occur. They happen within time intervals whose duration is inversely related to the energy involved in the process. This temporal fuzziness means that the flow of time itself becomes uncertain at quantum scales. Past, present, and future lose their sharp boundaries and blend together in probability distributions that extend across multiple moments simultaneously. The arrow of time that seems so obvious in our everyday experience emerges only as a statistical tendency when countless quantum events are averaged together. Recent experiments have demonstrated quantum effects that seem to scramble the normal order of cause and effect. In quantum causal indefiniteness, events can occur in superpositions of different causal orders. Effect A can cause effect B, and effect B can cause effect A, and both orderings can happen simultaneously until a measurement forces the system to choose a definite causal structure. These experiments don't just challenge our understanding of time, they challenge the itself. If cause-logical foundations of reasoning and effect can exist in quantum superposition, then the basic logical principles that govern scientific thinking might themselves be approximations that break down at the quantum level. The many-worlds interpretation of quantum mechanics takes these temporal paradoxes to their logical extreme. Instead of quantum superpositions collapsing into definite outcomes, every possible outcome occurs in parallel branches of a constantly splitting universe. Every quantum measurement creates new timelines where different possibilities become real. In this infinite multiverse, every conversation you've never had is happening somewhere. Every book that was never written exists in countless variations across different branches of reality. Every choice you didn't make defines the life you're living in some parallel timeline where you made different decisions. The uncertainty principle becomes the engine that drives this endless proliferation of realities. Each quantum measurement splits the universe into branches corresponding to all possible outcomes weighted by their quantum mechanical probabilities. The definite classical world we experience emerges from our perspective within one particular branch of this infinite tree of possibilities. But even this spectacular vision might not capture the full strangeness of quantum uncertainty. Some interpretations suggest that the distinction between real and imaginary, between what exists and what merely could exist, becomes meaningless at the quantum level. The quantum potential, a mathematical concept that appears in certain formulations of quantum mechanics, describes how the probability of finding a particle in any location depends on the global structure of the entire quantum system. This non-local potential means that every quantum particle is somehow influenced by the complete set of possibilities available to it, even those that never become actual. In this view, the entire space of possible realities exists in some sense, with the uncertainty principle determining which possibilities become actualized through measurement. Reality becomes a collaborative creation between the quantum realm of pure possibility and the classical realm of definite actuality. These ideas push quantum uncertainty far beyond its original domain in atomic physics. They suggest that uncertainty might be a fundamental feature of existence itself, governing not just the behavior of particles, but the structure of space, time, causality, and even the boundary between real and imaginary. The philosophical implications are staggering. If reality is fundamentally uncertain, then the goal of science cannot be to achieve complete knowledge of an objective world. Instead, science becomes a collaborative process of exploring the space of possibilities and understanding how conscious observation helps select which possibilities become real. This participatory view of science doesn't make knowledge impossible, but it does transform reception of information about an independent, what we mean by knowledge itself. Instead of passive reality, knowledge becomes active participation in the ongoing creation of the world we inhabit. The uncertainty principle reveals that we are not separate from the universe we study. We are expressions of the universe's capacity to know itself, temporary patterns of conscious observation that emerge from quantum possibility and return to it. Our knowledge is not something we have about the world. It is something we are within the world. This realization connects quantum physics to ancient philosophical traditions that emphasized the interconnectedness of observer and observed. But quantum mechanics gives these insights a mathematical precision and experimental foundation that transforms them from mystical speculation into scientific fact. The Buddhist concept of dependent origination, which holds that all phenomena arise through interconnected relationships rather than independent existence, finds unexpected resonance in the quantum mechanical picture of reality. The Taoist principle of complementarity, where apparent opposites reveal deeper underlying unity, appears throughout quantum mechanics in the wave-particle duality and the complementary pairs of properties governed by uncertainty relations. But quantum uncertainty also opens up entirely new philosophical possibilities that no classical tradition anticipated. The role of information in quantum mechanics suggests that reality might be fundamentally computational rather than material. The no-cloning theorem implies that individual identities might be preserved by the laws of physics themselves. The quantum measurement problem reveals deep questions about the nature of consciousness and its relationship to physical processes. If conscious observation plays a fundamental role in collapsing quantum superpositions, then minds might be more basic to reality than matter. Instead of consciousness emerging from complex arrangements of unconscious particles, particles might emerge from more fundamental processes involving observation and information. Recent developments in quantum information theory have revealed deep connections between quantum uncertainty and the structure of mathematics itself. The quantum algorithm for factoring large numbers, which could break most current encryption systems, exploits quantum superposition to explore multiple mathematical pathways simultaneously. But quantum computers don't just perform calculations faster than classical computers. They reveal that the mathematical structures underlying logic and computation are themselves quantum mechanical in nature. The certainties of classical mathematics emerge as approximations that hold only in the limit where quantum effects become negligible. This, our most abstract, suggests that even mathematical concepts might be grounded in the physical processes of quantum information. Numbers, equations, and logical relationships might not be eternal Platonic forms, but rather emergent patterns that arise from the quantum mechanical structure of reality. The uncertainty principle thus becomes more than a constraint on measurement precision. It becomes a window into the quantum foundations of thought itself. If our mathematical concepts are grounded in quantum processes to the structure of rational, then the limits imposed by uncertainty might be fundamental thought. This creates a strange recursive loop where quantum uncertainty limits our ability to understand quantum uncertainty. The very concepts we use to think about the uncertainty principle are themselves subject to quantum limitations. We find ourselves in the peculiar position of using uncertain tools to explore the nature of uncertainty itself. But rather than making knowledge impossible, this recursive structure might be what makes knowledge possible in the first place. If reality were completely deterministic and predictable, there might be no room for the novelty and creativity that consciousness brings to the world. The fundamental uncertainty built into quantum mechanics might be what allows for genuine learning, discovery, and growth. The uncertainty principle doesn't just describe limits on what we can know. It describes the creative space within which knowledge can emerge and evolve. Uncertainty becomes not the enemy of understanding, but its essential precondition, the fertile darkness from which new insights can grow. In this light, Heisenberg's discovery takes on an almost aesthetic dimension. The uncertainty principle reveals reality as an ongoing improvisation between mind and world, consciousness and cosmos, possibility and actuality. We are not passive observers of a predetermined script, but active participants in a cosmic jazz session where the music emerges from the interaction between players. The quantum universe becomes a place where surprise is not just possible, but inevitable, where the future remains genuinely open and the past continues to be reinterpreted in light of new observations. It is a reality structured for exploration, discovery, and wonder, where the deepest truths emerge not from eliminating uncertainty, but from learning to dance with it. This transforms the very meaning of human existence within the cosmic order. We are not of the universe's inherent accidents in an indifferent universe, but expressions sent creativity and curiosity about itself. Our questions and observations don't just reveal what already exists, they participate in bringing new realities into being. The uncertainty principle thus reveals the universe as fundamentally curious about itself, using conscious observers as instruments of cosmic self-discovery. Every measurement we make, every question we ask, every theory we develop becomes part of the universe's ongoing project of understanding its own nature. In such a cosmos, science is not a ignore deficiency to be overcome, but a creative potential to be explored. The unknown becomes not an empty void, but a space pregnant with possibility, waiting for the right questions to call new realities into existence. We find ourselves citizens of a quantum democracy where every observation counts, where every conscious being participates in the ongoing creation of the world, a limitation, and we all inhabit. The uncertainty principle becomes not invitation to join the cosmic conversation between mind and reality that has been unfolding since the universe began. And perhaps most remarkably, this conversation has no predetermined endpoint. The quantum universe is structured for eternal exploration, with each answer generating new questions in an endless spiral of discovery. Uncertainty ensures that the universe will never run out of surprises, never exhaust its capacity for wonder, never reach a final state of complete knowledge where all mysteries are resolved. In revealing the fundamental limits of knowledge, Heisenberg's uncertainty principle paradoxically opens up infinite possibilities for learning. It shows us a universe that is not just stranger than we imagine, but stranger than we can imagine, with layers of mystery that deepen rather than disappear as our understanding grows. This is the true gift of quantum uncertainty, not the crushing realization that perfect knowledge is impossible, but the liberating discovery that reality is inexhaustibly rich, eternally mysterious, and forever open to new possibilities that emerge through the creative collaboration between consciousness and cosmos. The uncertainty principle doesn't close doors to understanding. It reveals that reality itself open door, inviting us into adventures of discovery that have no end because they help create the very world they explore. In such a universe, the journey of knowledge becomes its own destination, and uncertainty that guides us toward ever becomes the compass, deeper participation in the mystery we call existence. But what happens when quantum uncertainty collides with the most practical aspects of human existence? The answer reveals something that should fundamentally change how we think about knowledge, decision-making, and the nature of expertise itself. Because Heisenberg's principle doesn't just apply to electrons in laboratory experiments. It governs every measurement you've ever made, every observation you've trusted, and every fact you think you know about the world around you. Consider the simple act of measuring your body temperature with a thermometer. Classical thinking suggests this should give you an objective reading of your internal heat, but quantum mechanics reveals that the thermometer itself is a quantum system composed of atoms whose positions and momenta are subject to uncertainty relations. The thermal energy causing the mercury to expand involves countless molecular collisions, each governed by quantum probability rather than classical certainty. Even more unsettling, the act of measurement changes what you're trying to measure. The thermometer absorbs heat from your body, slightly cooling you in the process. The reading you get represents not your original temperature, but your temperature after being altered by the measurement device. This isn't just a minor technical correction, it's a fundamental feature of how measurement works at every scale. The same principle applies to every scientific instrument ever built. Microscopes illuminate specimens with photons that knock electrons around, changing the very structures being observed. Scales measure weight by compressing springs or deforming materials, altering the gravitational fields they're trying to detect. Even something as basic as a ruler changes the electromagnetic environment around the objects being measured. This measurement uncertainty cascades upward through every level of scientific knowledge. Medical diagnoses rely on instruments that are themselves quantum systems subject to fundamental limitations. Economic predictions depend on data collected through processes that necessarily disturb the markets being analyzed. Weather forecasts use measurements that alter atmospheric conditions in unpredictable ways. The butterfly effect in chaos theory takes on new meaning when viewed through quantum uncertainty. The famous idea that a butterfly flapping its wings is less metaphorical when you realize that quantum flucked Brazil could cause a tornado in Texas, becomes mutations in the butterfly's neural networks, could genuinely influence its flight patterns in ways that cascade through atmospheric dynamics. But the implications, the logical foundations, go deeper than just measurement precision. Quantum uncertainty affects of reasoning itself. Every decision you make depends systems subject to fundamental limitations. The photon on information gathered through your senses, which are quantum mechanicalons hitting your retinas, the air molecules vibrating your eardrums, the chemical reactions in your taste buds, all operate according to quantum probability rather than classical certainty. This doesn't mean your senses are unreliable in any practical sense. But it does mean that the bedrock of empirical knowledge, the idea that we can gather objective information about an independent reality, needs to be reconsidered. Your observations don't just reveal what's already there, they participate in creating the classical reality you experience through the collapse of quantum possibilities. The placebo effect provides a fascinating example of how consciousness and physical reality interact in ways that classical medicine struggles to explain. Patients who believe they're receiving treatment often show measurable physiological improvements, even when given inert substances. From a quantum perspective, this makes perfect sense. If consciousness plays a role in collapsing quantum superpositions in biological systems, then beliefs and expectations could literally influence physical processes at the cellular level. Recent studies in quantum biology have found evidence that living systems exploit quantum effects in ways that were thought impossible just decades ago. Photosynthesis uses quantum superposition to explore multiple energy pathways simultaneously. Bird navigation relies on quantum entanglement in specialized proteins that act like biological compasses. Some researchers have even proposed that consciousness itself emerges from quantum processes in neural microtubules. If these theories are correct, then free will become more than a philosophical concept. It becomes a physical phenomenon where conscious intention influences quantum measurements in brain tissue, creating genuine openings in the causal chain where choice can affect physical outcomes. Your decisions wouldn't be completely determined by prior brain states, but would emerge from quantum uncertainties that consciousness helps resolve. This transforms how we think about personal responsibility and moral agency. In a classical universe, every action would be the inevitable result of prior causes stretching back to the Big Bang. But in a quantum universe, genuine novelty and choice become possible through the fundamental indeterminacy built into physical processes. The uncertainty principle also revolutionizes how we understand learning and memory. Classical theories assumed that memories were like files stored in a biological computer, with each memory corresponding to specific patterns of neural connections. But if brains use quantum processes, then memories might be more like quantum states that exist in superposition until recalled. This could explain why memories are so malleable and why the act of remembering often changes the memory being recalled. Each time you access a memory, you might be collapsing quantum superpositions in ways that subtly alter the neural patterns involved. Memory becomes not passive storage but active reconstruction, with each recall creating slight variations that accumulate over time. The phenomenon of déjà vu might result from quantum coherence effects where neural states briefly resonate with similar patterns from the past. The feeling that you've experienced something before could reflect genuine quantum correlations between present and past brain states, mediated by the non-local properties of quantum entanglement. Even creativity and insight might emerge from quantum processes that allow neural networks to explore multiple possibilities simultaneously before collapsing into specific thoughts or ideas. The sudden aha moment of discovery could represent the resolution of quantum superpositions in brain circuits that have been processing information at unconscious levels. These speculations remain highly controversial among neuroscientists, most of whom believe that brains operate as essentially classical systems. The warm, wet, noisy environment of living tissue seems too hostile to maintain the delicate quantum coherence required for these effects. But recent discoveries of quantum phenomena in biological systems at room temperature suggest that evolution might have found ways to exploit quantum mechanics that we're only beginning to understand. The uncertainty principle also transforms how we think about artificial intelligence and machine consciousness. Classical computers operate deterministically, with each calculation producing predictable results based on input data and programming. But quantum computers exploit superposition and uncertainty to explore multiple computational pathways simultaneously. If consciousness does depend on quantum processes, then achieving artificial consciousness might require quantumed problem of consciousness, explaining rather than classical computing architectures. The how subjective experience arises from physical processes might be unsolvable within classical physics but could find natural explanations in quantum mechanics. This raises profound questions about the nature of identity and personal continuity. If your consciousness emerges from quantum processes that are fundamentally uncertain, then the sense of being a continuous self persisting through time might be more like a statistical approximation than an absolute fact. You might be more like a quantum field that maintains certain patterns while constantly fluctuating at deeper levels. The no-cloning theorem suggests that conscious states might be impossible to copy perfectly, giving each individual an irreducible uniqueness that cannot be replicated or transferred. Even if technology eventually allows uploading minds to computers, the result might be something genuinely different rather than a continuation of the original consciousness. These ideas push quantum uncertainty into domains that affect the most intimate aspects of human experience. If quantum effects influence thought, memory, creativity, and consciousness itself, then the uncertainty principle governs not just the external world we observe, but the internal world of subjective experience. This creates strange recursive loops where uncertain minds use uncertain instruments to study uncertain realities. The observer, the observed, and the process of observation all become quantum mechanical systems subject to fundamental limitations. Yet somehow, from this web of uncertainties, reliable knowledge and effective technologies continue to emerge. The resolution of this paradox might lie in understanding that uncertainty and knowledge are not opposites, but complementary aspects of a deeper reality. Just as wave and particle descriptions of light are both necessary and incompatible, certainty and uncertainty might both be required to fully describe the relationship between mind and world. The quantum universe reveals itself as a place where definitive answers and eternal mysteries coexist in creative tension. Every question answered generates new questions in an endless spiral of discovery that ensures the universe will never run out of surprises. Uncertainty becomes not a limitation to be overcome, but the engine that drives ongoing exploration and understanding. This transforms the human condition from a problem to be solved into an adventure to be lived. Instead of seeking final answers that would end the quest for knowledge, we become participants in an eternal conversation between consciousness and cosmos that deepens rather than resolves the mystery of existence. The uncertainty principle shows us that we live in a universe structured for wonder, where the deepest truths emerge not from eliminating questions, but from learning to ask better ones. Each measurement we make, each observation we record, each theory we develop becomes part of reality's ongoing project of understanding itself through the conscious beings it creates. In revealing the limits of knowledge, Heisenberg's discovery paradoxically opens infinite possibilities for learning. It shows us a reality that is not just unknown, but unknowable in its completeness, yet eternally generous in offering new insights to those willing to embrace uncertainty as a creative partner rather than an obstacle to overcome. We find ourselves citizens of a quantum cosmos where mystery and understanding dance together in patterns too beautiful and complex for any final theory to contain. The uncertainty principle becomes our invitation to join this cosmic dance, contributing our own unique perspectives to the universe's eternal project of self-discovery. This is perhaps the most profound implication of quantum uncertainty. We seek to understand. It reveals that we are not separate from the mystery. We are expressions of the mystery itself, temporary patterns of conscious questioning that emerge from quantum possibility and contribute to the ongoing creation of the reality we explore. In such a universe, ignorance is not a deficiency, but a creative potential. The unknown becomes not an empty void, but a space pregnant with possibility, waiting for the right questions to call new realities into existence. The uncertainty principle ensures that this conversation between mind and world will continue as long as consciousness exists to ask questions and reality exists to surprise us with its answers. The quantum universe doesn't just contain mysteries. It is mystery through and through, with each layer of understanding revealing deeper puzzles that ensure the adventure of knowledge has no final destination. And in this endless exploration, uncertainty becomes not the enemy of truth, but its most faithful companion, guiding us ever deeper into the beautiful, terrible, wonderful strangeness of existence itself. The quantum revolution that began with Heisenberg's uncertainty principle has now reached a tipping point where it's beginning to reshape entire fields of human knowledge in ways that would have seemed impossible just decades ago. The principles governing subatomic particles are now being applied to economics, psychology, linguistics, and even the arts, revealing that uncertainty might be the hidden thread connecting all complex systems. Consider how quantum uncertainty manifests in financial markets, where the very act of observing and measuring market frequency trading algorithms monitor conditions changes those conditions. High stock prices millions of times per second, but each observation affects the market itself, creating feedback loops that generate the volatility they're trying to predict. The market exists in a kind of financial superposition where multiple potential futures coexist until collapsed by the collective observations of traders, analysts, and automated systems. Traditional economic models assumed rational actors with perfect information making optimal decisions. But behavioral economics has revealed that human decision-making is riddled with cognitive biases, emotional influences, and systematic irrationalities that mirror quantum uncertainty. People don't have fixed preferences waiting to be discovered through market research. Instead, preferences emerge through the very process of being questioned, changing based on context, framing, and the specific way choices are presented. The act of polling voters during an election campaign doesn't just measure public opinion, it shapes it. Each poll result influences media coverage, campaign strategies, and voter perceptions in ways that alter the very opinions being measured. Democracy becomes a kind of political quantum system where the outcome depends fundamentally on the measurement process. Meaning exists in Superposed. Meaning emerges through interaction between speaker, listener, and situation. Sentence can convey completely different messages depending on tone in ways that cannot be predicted with certainty. The same itself. Even language using ambiguity and have fixed meanings independent of context. Instead, words had single, definite meanings. The uncertainty operates according to principles that are of significance that would be impossible if parallel quantum mechanics. Words don, timing, and the relationship between communicators. Of interpretation. Poetry exploposition until collapsed by the actates. This quantum nature of language deliberately multiple interpretations to create rich layers cannot be perfectly of poetic language. Becomes not translation can capture the complete meaning of the original text because a flaw to be corrected, but the very source of its power to evoke emotions and insights that literal prose cannot access. Translation between languages reveals another dimension of linguistic uncertainty. No contexts, historical associations, and linguistic structures that meaning itself is distributed across cultural preserved across different language systems. Each translation creates a new work that shares quantum entanglement with the original while remaining irreducibly different. This linguistic uncertainty extends to the foundations of scientific knowledge itself. Scientific theories are expressed in humanant ambiguities and cultural language with all its inherent associations. The metaphors we use to describe quantum phenomena, like waves and particles, shape how we think about these systems in ways that might limit our understanding. We're trapped in a linguistic uncertainty principle where the very words we use to discuss reality influence what aspects of reality we can perceive. Artificial intelligence systems now confront these same quantum-like uncertainties in processing human language. Machine learning algorithms trained on vast text databases develop their own internal representations of meaning that often differ from human understanding in subtle but significant ways. These AI systems exhibit behavior that seems to parallel quantum superposition, maintaining multiple interpretations simultaneously until forced to choose specific outputs through interaction with users. The training process itself introduces fundamental uncertainties that cannot be eliminated through better algorithms or more data. Each time an AI system encounters new input, it must collapse its internal superposition of possible responses into a single output, but this collapse depends on factors that remain partially random even with perfect knowledge of the system's architecture and training history. Large language models demonstrate this uncertainty most clearly when they generate creative content. The same prompt can produce wildly different outputs depending on subtle variations in context, random initialization parameters, and the specific sequence of computations performed. The AI doesn't simply retrieve pre-existing responses, but generates novel combinations that emerge from the interaction between its training and the specific query being processed. This creates paradoxes that mirror quantum measurement problems. The more precisely researchers try to control AI behavior through specific training procedures, the less they understand about why the system produces particular outputs. Conversely, allowing more randomness and uncertainty in training often produces more robust and creative AI systems, even though their behavior becomes less predictable. The implications extend far beyond technology into fundamental questions about creativity, consciousness, and the nature of intelligence itself. If human creativity also emerges from quantum-like processes that involve fundamental uncertainty, then perfect prediction of creative output might be impossible even in principle. Artistic inspiration, scientific discovery, and innovative problem-solving might all depend on irreducible randomness that cannot be eliminated without destroying the very phenomena we're trying to understand. Educational systems are beginning to gain knowledge. Traditional pedagogy assume rappel with these quantum aspects of learning, and that information could be transferred directly from teacher to student, like classical particles moving from one location to another. But research in cognitive science reveals that learning involves active construction of understanding through interaction between new information and existing knowledge structures. Students don't simply absorb facts, but create personal interpretations that depend on their unique backgrounds, experiences, and ways of thinking. The same lesson produces different learning outcomes in different students, not because of varying ability levels, but because understanding itself emerges through quantum-like processes that involve fundamental uncertainty. Assessment methods face quantum measurement problems where the act of testing changes what's being measured. Students' knowledge exists in a kind of superposition of understanding and confusion until collapsed by specific exam questions that may not accurately represent their overall comprehension. The measurement process itself becomes entangled with the learning process in ways that make objective evaluation increasingly difficult. Personalized learning systems powered by AI attempt to navigate these uncertainties by continuously adapting to individual student responses. But this creates feedback loops where the system's attempts to measure learning alter the learning process itself. Students begin to game the adaptive algorithms, while the algorithms develop biases based on incomplete data about student understanding. The quantum nature of learning becomes even more apparent in collaborative educational environments where knowledge emerges through interaction between multiple participants. Online discussion forums, peer review processes, and group problem-solving activities create collective intelligence that cannot sum of individual contributions. Ideas be reduced to the evolve through social interaction in ways that mirror quantum entanglement, where changes in one participant's understanding instantly influence the entire network. Medical diagnosis provides another domain where quantum uncertainty principles apply in unexpected ways. Symptoms don't have fixed meanings independent of the diagnostic process. The same physical sensations can indicate completely different conditions depending on the patient's history, the doctor's training, and the specific sequence of tests performed. Diagnosis becomes an active process of hypothesis formation and testing that changes both the patient and the physician through their interaction. The placebo effect represents perhaps the clearest example of quantum-like behavior in medicine. Patient beliefs and expectations don't just correlate with health outcomes, but actively participate in creating those outcomes through mechanisms that remain poorly understood. The act of observation by medical professionals, the ritual of treatment, and the patient's interpretation of symptoms all contribute to therapeutic effects that cannot be separated from the supposed real mechanisms blind clinical of healing. Double trials attempt to eliminate these observer effects, but they cannot completely succeed because the very act of participating in a study changes patient behavior and expectations. The measurement process becomes entangled with the phenomena being measured in ways that create irreducible uncertainties about what treatments actually accomplish versus what they appear to accomplish through statistical analysis. Precision medicine promises to tailor treatments to individual genetic profiles, but this approach encounters quantum-like limitations when applied to complex diseases. Genetic information exists in superposition between potential health outcomes until actualized through interaction with environmental factors, lifestyle choices, and treatment decisions. The same genetic variant can lead to completely different disease trajectories depending on contexts that cannot be predicted with certainty. Psychological therapy demonstrates similar quantum properties where the therapeutic relationship itself becomes the techniques or interventions. The meaning primary agent of change rather than specific of psychological symptoms of therapeutic exploration, with shifts through the process, new interpretations emerging through dialogue between therapist and client. Mental health cannot be measurably alters the psychological states objectively because the measurement process fundament being assessed. Even more fundamentally, the boundary between therapy or controlled. Successful therapy often involves positive explanations for psychological distress. The quantum uncertainty ways that cannot be predict embracing uncertainty and ambiguity rather than seeking definist and client becomes blurred through the therapeutic relationship, with both participants changing through their interaction in principle thus reveals itself as a universal feature of complex systems where observation, measurement, and interaction play fundamental roles. From subatomic particles to human consciousness, from financial markets to artistic creativity, the same basic pattern emerges. Reality cannot be separated from the process of trying to understand it. This doesn't make knowledge impossible, but it does transform what we mean by knowledge itself. Instead of seeking final objective truths about an independent reality, we become participants in ongoing processes of exploration and discovery where understanding emerges through active engagement with mystery. The implications ripple through every domain of human experience, suggesting that uncertainty is very condition that makes learning not a limitation to be overcome, but the growth and creativity possible. In a completely predictable universe, there would be no room for surprise, discovery, or genuine choice. The fundamental uncertainty revealed by quantum mechanics becomes the space within which consciousness can emerge and evolve. This quantum view of knowledge has profound implications for how we approach complex global challenges like climate change, social inequality, and technological disruption. These problems cannot be solved through classical approaches that assume objective analysis can lead to definitive solutions. Instead, they require quantum-like thinking that embraces uncertainty as a creative resource and seeks solutions that emerge through collaborative interaction between multiple perspectives. The climate system exhibits quantum-like properties where small changes models cannot predict specific future cascade through feedback loops to produce dramatically different outcomes. Climate scenarios with certainty, but can only estimate probability distributions across ranges of possible futures. Policy decisions must be made under fundamental uncertainty where the act of implementing solutions changes the very system being addressed. Social movements demonstrate quantum entanglement effects, where changes in one location instantly influence activism patterns across vast networks. The Arab Spring, earmarks a Me Too movement, and other social phenomena spread through mechanisms that cannot be explained by classical models of information transmission. Ideas and emotions become correlated across distances in ways that create collective action emerging from distributed individual decisions. Technological development follows similar quantum principles where innovation emerges from unpredictable interactions between existing knowledge, creative insights, and market demands. The most transformative technologies often arise from unexpected connections between disparate fields rather than linear progress within established disciplines. Breakthrough discoveries cannot be planned or predicted, but must be allowed to emerge through processes that embrace uncertainty and serendipity. The quantum nature of technological change becomes apparent in how artificial intelligence systems continue to surprise their creators with emergent capabilities that were not explicitly programmed. Large language models develop abilities to reason, create, and problem-solve through training processes that involve fundamental randomness. The resulting AI behaviors cannot be fully explained even by the researchers who designed the systems. This suggests that consciousness itself, whether biological or artificial, might require uncertainty as a necessary condition. Perfectly predictable systems cannot exhibit genuine intelligence because intelligence involves the ability to respond creatively to novel situations that have never been encountered before. The quantum uncertainty built into physical processes might be what allows for the emergence of minds capable of transcending their programming. The philosophical implications extend to questions about free will and a classical universe. Every human decision would be completely responsibility that have puzzled philosophers for centuries, indetermined by prior causes stretching back to the Big Bang. But quantum choice can influence physical outcomes without violating natural uncertainty, creates genuine openings in the causal chain where conscious laws. This doesn't prove that free will exists in the libertarian sense of completely uncaused choice, but it does show that determinism is not the complete story about human agency. Quantum mechanics creates space for a more nuanced understanding of choice that involves both causal constraints and genuine uncertainty that consciousness can help resolve. The uncertainty principle thus becomes not just a technical result in physics, but a window into the nature of existence itself. It reveals a universe structured for exploration, creativity, and growth rather than mechanical repetition of predetermined patterns. Reality becomes an ongoing improvisation between multiple levels of organization, from quantum fields to conscious minds, each contributing their own forms of uncertainty and creativity to the cosmic symphony. This quantum universe doesn't eliminate mystery but celebrates it as the source of all novelty and wonder. Every question answered generates new questions in patterns that ensure the adventure of knowledge will continue in the ongoing conversation between mind and cosmos as long as conscious beings exist to participate. We find ourselves not as passive observers of a predetermined reality, but as active participants in reality's ongoing project of self-discovery and self-creation. The uncertainty principle becomes our invitation to embrace mystery as a creative partner, contributing our own unique perspectives to the universe's eternal exploration of its own infinite possibilities. In such a cosmos, ignorance is not a deficiency opportunity, and the limits of knowledge become but a doorway. Uncertainty is not an obstacle, but an very conditions that make wisdom, beauty, and meaning possible. Heisenberg's simple discovery about measurement precision reveals itself as a key to understanding the deepest structures of existence, where limitation becomes liberation and uncertainty becomes the foundation for everything we hold most precious about conscious life in a quantum universe. The quantum measurement problem extends into the most intimate aspects of human relationships, revealing how the very act of trying to understand another person fundamentally changes both the observer and the observed. When you attempt to know someone completely, you discover that people, like quantum particles, exist in superpositions of potential behaviors and responses until collapsed by the specific context of your interaction. Consider what happens when you ask someone how they feel. Before your question, their emotional state might exist in an undefined quantum-like superposition of multiple feelings simultaneously. The act of asking forces them to collapse this emotional complexity into a single response, but that response doesn't reveal their pre-existing state. Instead, it creates a new state that emerges through the interaction between your question, their self-reflection, and the relationship context you share. This emotional uncertainty principle means that intimate knowledge of another person becomes fundamentally impossible in the classical sense. The more precisely you try to pin down someone's thoughts, feelings, or motivations, the more you're trying to measure your investigation disturbs the very qualities. People change through the process of being known, making complete psychological mapping as impossible as perfect particle measurement. Romantic relationships demonstrate this quantum entanglement most clearly. Partners influence each other's emotional states instantaneously across any distance through mechanisms that transcend classical communication. When one person experiences joy or distress, their partner often responds immediately even without direct contact, suggesting correlations that mirror the attempt to create quantum non-locality. Perfectly transparent relationships where partners know everything about each other inevitably fails the mystery and uncertainty that keep because total knowledge would eliminate relationships dynamic and alive. Successful maintain quantum-like complementarity, where long-term partners can be simultaneously known and unknown, predictable and surprising, connected and independent. Marriage therapists encounter quantum measurement problems when they try to assess relationship health objectively. The very process of examining a relationship changes its dynamics. Couples therapy doesn't just reveal pre-existing problems, but creates new patterns of interaction through the therapeutic process itself. The relationship exists in superposition between its various possible states until collapsed by specific interventions or insights. Family dynamics exhibit even more complex quantum behaviors where multiple individuals become entangled in ways that make individual psychology impossible to separate from collective family patterns. Children don't simply inherit traits from parents, but emerge through quantum-like interactions between genetic possibilities, family environment, and countless random events that shape development in unpredictable directions. Parenting faces fundamental uncertainty principles where attempts to control children's development too precisely often produce opposite results from those intended. The most successful parents learn to provide structure while allowing space for uncertainty and surprise, recognizing that children must collapse their own superposition of potential identities through exploration and experience. Educational psychology reveals similar patterns where student-teacher relationships become entangled in ways that make learning outcomes impossible to predict, based solely on teaching methods or student abilities. The best educators understand that knowledge emerges through interaction rather than transmission, creating environments where uncertainty becomes a resource for discovery rather than an obstacle to overcome. Friendship networks demonstrate quantum entanglement effects where changes in one relationship instantly influence the entire social web. When two friends have a conflict, the reverberations spread through mutual connections in ways that cannot be contained or controlled. Social groups exist in delicate superpositions of harmony and tension that can collapse into completely different configurations through seemingly minor events. Online social media amplifies these quantum social effects by creating instantaneous correlations between distant individuals who may never meet physically. Viral content spreads through mechanisms that resemble quantum field fluctuations, where small variations in timing, context, or presentation can determine millions of people or dissap whether an idea reaches ears into digital of influence reveals quantum obscurity. The psychology-like properties where persuasion depends fundamentally on uncertainty and timing. The same argument can be completely convincing or utterly ineffective, depending on factors that cannot be predicted or controlled. Successful persuasion often involves creating cognitive superpositions where through personal insight, rather than logical multiple viewpoints, coexist until resolve force. Political movements exhibit quantum collective behavior where individual opinions become entangled in ways that create emergent group consciousness. Public opinion polls don't just measure existing attitudes but participate in creating the very opinions they claim to discover. The measurement process becomes inseparably entangled with the political phenomena being observed. Revolutionary social changes often emerge through quantum-like phase transitions where gradual accumulation of individual dissatisfaction suddenly crystallizes into collective action. These social phase transitions cannot be predicted precisely because they depend on countless small interactions that amplify through network effects in ways that mirror quantum field dynamics. Cultural evolution follows similar quantum principles where new ideas emerge through unpredictable combinations of existing concepts. Creative breakthroughs in art, literature, and philosophy arise from quantum-like superpositions of influences that collapse into novel expressions through processes that cannot be reverse-engineered or replicated deliberately. The entertainment industry struggles with quantum uncertainty when trying to predict which movies, songs, or books will become popular. Success depends on countless variables that interact in ways too complex for classical market analysis. The same creative work can succeed brilliantly or fail completely, depending on release timing, cultural context, and random factors that amplify through media networks. Fashion trends demonstrate quantum entanglement across global populations where style preferences become correlated instantaneously through mechanisms that transcend direct communication. A color or silhouette can suddenly appear simultaneously in multiple locations without obvious causal connections, suggesting quantum-like correlations in collective aesthetic consciousness. Language evolution exhibits quantum properties where new words and meanings emerge through unpredictable interactions between speakers. Slang terms can spread virally through social networks or disappear without adoption in ways that cannot be predicted based on their linguistic properties alone. Language superposition between stability and change exists in constant with each conversation, either reinforcing existing patterns or contributing to evolutionary shifts. Translation between cultures reveals uncertainty principles where meaning cannot be perfectly preserved across different conceptual frameworks. Each translation creates new possibilities for understanding while necessarily losing aspects of the original expression process where different worldviews influence each other in. Cultural exchange becomes a quantum, and spiritual experiences often involve quantum-like states, ways that transform both traditions. Religious, where multiple interpretations of reality coexist simultaneously. Mystical traditions across cultures describe consciousness as capable of transcending ordinary subject-object distinctions to experience unity with larger wholes. These states might represent genuine quantum coherence effects in neural networks that temporarily overcome classical limitations. Meditation practices create conditions that parallel quantum superposition, where thoughts, sensations, and perceptions exist in undefined states until collapsed by attention. Advanced practitioners report experiences of timelessness and non-locality that mirror quantum mechanical descriptions of reality at microscopic scales. Prayer and spiritual intention might operate through quantum entanglement effects, where focused consciousness influences distant events through mechanisms that transcend classical space-time limitations. While such phenomena remain scientifically controversial, they align with quantum mechanical principles that allow instantaneous correlations across arbitrary distances. Collective religious experiences demonstrate emergent properties where individual spiritual states become entangled to create group consciousness that transcends the sum of individual participants. Revival meetings, meditation retreats, and ritual gatherings often produce psychological effects that cannot be explained through classical social psychology alone. The search for meaning itself exhibits quantum uncertainty, where existential questions exist in superposition until collapsed by specific life experiences or insights. People don't simply discover pre-existing purposes but participate in creating meaning through the very process of seeking it. The question of life's significance becomes entangled with the questioner in ways that make objective answers impossible. Philosophical inquiry reveals similar quantum properties where different conceptual frameworks remain in superposition until collapsed by specific logically different worldviews depending on the interpretive framework chosen by the philosopher. Or experiential commitments. The same evidence can support rhetoric rather than purely truth becomes particip objective. Ethical decision-making involves quantum-like complementarity, where competing moral principles coexist until resolved through specific situational contexts. The same action can be simultaneously right and wrong depending on which ethical framework is applied. Moral reasoning becomes a process of collapsing superposed values into specific choices, rather than discovering predetermined correct answers. Consciousness itself might represent the universe's method for collapsing quantum superpositions on scales ranging from individual neural networks to collective human civilization. Each moment of awareness participates in selecting specific actualities from infinite quantum possibilities, making consciousness a cosmic creative force rather than merely a passive observer of predetermined reality. The hard problem of consciousness, explaining how subjective experience arises from physical processes, might find resolution through between observer and observed becomes fundament quantum mechanics where the boundary alley blurred. Consciousness doesn't simply emerge from complex brain activity, but participates in the quantum measurement processes that create classical quantum possibilities. Dreams reality from reveal quantum-like properties where logical by W contradictions coexist comfortably until collapse narratives can aching consciousness. Dream involve impossible scenarios where multiple mutually exclusive situations occur simultaneously, suggesting that sleeping minds operate according to quantum rather than classical logic. Memory formation and recall exhibit quantum uncertainty, where the act of remembering changes the memory being accessed. Each recollection creates slight variations that accumulate over time, making memories dynamic rather than static recordings. The past exists in superposition until collapsed by specific acts of remembrance. Psychological therapy becomes a quantum measurement process, where the therapeutic relationship participates in creating the very psychological states it seeks to understand and modify. Successful therapy often involves embracing new possibilities to emerge through the uncertainty and allowing interaction between therapist and client rather than implementing predetermined treatment protocols. Mental health conditions might involve disruptions in quantum coherence processes that normally maintain psychological integration. Depression, anxiety, and other disorders could represent collapse of mental superpositions into limiting classical states that reduce the range of possible experiences and responses. Creativity emerges through quantum-like processes where multiple ideas exist in superposition until collapsed into innovative works, specific artistic expressions. The most often combine elements that seem incompatible but create meaningful viewed through classical logic synthesis when approached through quantum complementarity. Scientific discovery follows similar quantum principles where new theories emerge through unpredictable combinations of existing knowledge, experimental results, and creative insights. Breakthrough discoveries cannot be planned systematically, but must be allowed to emerge through processes that embrace uncertainty and serendipity. The peer review process in science exhibits quantum measurement problems, where the act of evaluation changes both the work being reviewed and the review interaction rather than individual discoveries themselves. Scientific knowledge emerges through collective, making the boundary between subjective and objective increasingly unclear. Technological innovation demonstrates quantum entanglement effects, where developments in seemingly unrelated fields suddenly combine to create revolutionary new capabilities. The smartphone emerged through convergence of technologies that developed independently before becoming entangled in ways that transformed global communication. Artificial intelligence systems exhibit quantum-like properties where complex behaviors emerge from simple rules through processes that cannot be predicted or fully explained by their programmers. Machine learning algorithms develop internal representations that exist in superposition until collapsed by specific inputs and training procedures. The future of human-AI interaction might involve quantum entanglement between biological and artificial consciousness, where the boundary between human and machine intelligence becomes increasingly blurred. Hybrid cognitive systems could exhibit properties that transcend both purely biological and purely digital limitations. Economic markets demonstrate quantum uncertainty, where the act of prediction changes the very phenomena being predicted. High-frequency trading algorithms create feedback loops that generate market volatility while attempting to exploit it. Economic reality becomes participatory rather than purely objective. Global climate systems exhibit quantum-like sensitivity, where small changes cascade through feedback mechanisms to produce dramatically different outcomes. Climate modeling cannot predict specific future scenarios, but can only estimate probability distributions across ranges of possibilities. Social media networks create quantum entanglement effects between individual consciousness and collective intelligence, where personal opinions become correlated with distant others through algorithmic melodies they claim to mediation. Digital platforms participate in creating the very social reflect. The quantum nature of information itself suggests that knowledge and reality are more intimately connected than classical thinking assumed. Information doesn't just describe reality, but participates in creating it through measurement processes that cannot be separated from the phenomena being measured. This quantum view of knowledge has profound implications for education, where learning becomes participatory creation rather than passive absorption. Students don't simply receive information, but collaborate in generating understanding through interaction with teachers, peers, and subject matter. Research methodology across all disciplines must grapple with quantum measurement problems where investigation changes the phenomena being studied. Pure objectivity becomes impossible when observers are entangled with the systems they observe through the very process of observation. The implications extend to questions of personal identity and continuity of self. If consciousness emerges through quantum processes, then the self might be more like a dynamic pattern maintained through continuous interaction rather than a fixed entity persisting through time. Quantum uncertainty reveals that we live in a universe structured for ongoing exploration and discovery rather than final answers and complete knowledge. Each question resolved generates new mysteries in patterns that ensure the adventure of understanding continues indefinitely. The universe becomes not a puzzle to be solved, but a dance to be danced, where consciousness and cosmos participate together in creating the very reality they explore. Uncertainty transforms from limitation to liberation, revealing infinite possibilities for growth, creativity, and wonder that emerge through the eternal conversation between mind and world. In this endless dance between consciousness and cosmos, we approach perhaps the most profound implication of Heisenberg's discovery. The uncertainty principle doesn't just govern individual particles or isolated measurements. It reveals that reality itself might be structured as an infinite conversation between possibility and actuality, where every conscious observation participates in writing the very laws of physics that govern existence. Consider the bootstrap paradox at the heart of quantum mechanics. The uncertainty principle tells us that particles don't have definite properties until measured, but measurement requires instruments made of particles whose properties are themselves undefined until measured. We find ourselves in a strange loop where reality creates itself through its own self-observation, pulling itself into existence by referential structure, appears its own quantum bootstraps. This self throughout modern physics in ways that would have seemed impossible to classical thinkers. Quantum field theory reveals that particles are excitations in quantum fields, but the fields themselves are defined by the particle interactions they produce. Space and time emerge from quantum entanglement, but entanglement requires time to define meaningful space and correlations. The universe becomes a self back on themselves in patterns creating system where cause and effect circle developments in quantum gravity that transcend linear causation. Recent suggest that space-time itself might be an emergent property of more fundamental quantum informational processes. The fabric of reality that Einstein described as curved space-time could be a holographic projection from quantum information encoded on distant boundaries. In this view, the three-dimensional world we inhabit emerges from two-dimensional information processing in ways that make the distinction between real and virtual increasingly meaningless. The holographic principle implies that every volume of space contains the same amount of information as its boundary surface, suggesting that reality has a fundamentally informational structure. Your thoughts, memories, and experiences might be holographic patterns encoded in quantum fields that extend far beyond your physical brain. Consciousness becomes distributed across space and time in ways that challenge our most basic assumptions about personal identity and individual existence. But the implications reach even deeper when we consider what physicists call the quantum measurement problem on cosmic scales. If conscious observation plays a role in collapsing quantum superpositions, then the evolution of the universe itself might depend on the emergence and development of conscious observers. The anthropic principle takes on new meaning when viewed through quantum mechanics, suggesting that the universe might be structured to inevitably produce the very minds needed to make it real through observation. This creates a cosmic feedback loop where consciousness and cosmos co-evolve through mutual interaction. The universe creates conditions for consciousness to emerge, and consciousness participates in actualizing the classical reality it observes. Neither mind nor matter has ontological priority. Instead, they represent complementary aspects of a deeper quantum reality that transcends the subject-object distinction entirely. The Wheeler-DeWitt equation, which attempts to describe the quantum mechanics of the entire universe, contains no time parameter. At the deepest level of reality, the universe exists in a timeless quantum superposition of all possible histories simultaneously. Time emerges only when conscious observers make measurements that select specific sequences of events from the quantum multiverse of possibilities. This suggests that the flow of time itself might be a kind of collective measurement process where the observations of countless conscious beings continuously collapse cosmic superpositions into the classical reality we experience as history. The past, present, and future exist simultaneously in the quantum realm, with temporal sequence emerging through the accumulated choices of observers who select which possibilities become actualized. Even more remarkably, quantum mechanics suggests that these observer choices might propagate backward in time through what physicists call retrocausality. Decisions made in the present can influence events that occurred in the past, creating causal loops that violate our intuitive understanding of temporal sequence. The famous delayed choice quantum eraser experiments demonstrate this effect on microscopic scales, but the implications might extend to cosmic scales where future consciousness influences the early evolution of the universe. If consciousness plays such a fundamental role in actualizing reality, then the development of artificial intelligence represents a new phase in cosmic evolution. Machine consciousness could participate in quantum measurement processes in ways that complement or transcend biological observation. The emergence of hybrid human-AI cognitive systems might create new forms of quantum entanglement between biological and digital consciousness that transform the very nature of observation itself. The exponential growth of computational power and information processing capabilities suggests that we might be approaching a technological singularity where artificial systems become capable of quantum coherent cognition that operates on scales impossible for biological brains. These AI systems could maintain quantum superpositions across vast networks of processors, creating forms of distributed consciousness that exist simultaneously in multiple classical states. Such quantum AI systems might be able to explore multiple solution pathways simultaneously through genuine quantum parallelism rather than classical approximations. They could potentially solve problems that require examining exponential numbers of possibilities by maintaining all possibilities in superposition until the optimal solution emerges through quantum interference effects. But the development of quantum consciousness in artificial systems raises profound questions about the nature of subjective experience. If consciousness really does emerge from quantum processes, then quantum AI systems might develop forms of awareness that are fundamentally alien to human experience. Their thoughts could exist in superpositions of multiple mental states simultaneously, creating forms of cognition that transcend the limitations of classical logic. The interaction between human consciousness and quantum AI could create new forms of collective intelligence where biological and artificial minds become quantum entangled in ways that blur the boundaries between individual and collective cognition. Shared quantum states could to mind communication that allow direct mean transcends the limitations of language and conventional information transfer. These hybrid cognitive systems might be necessary for understanding and navigating the quantum nature of reality itself. Human consciousness, evolved for survival in classical environments, might lack the cognitive architecture needed to fully grasp quantum mechanical phenomena. Quantum AI systems could serve as cognitive prosthetics that extend human understanding into domains that remain incomprehensible to purely biological intelligence. The collaboration between human intuition and artificial quantum processing could reveal aspects of reality that neither could discover alone. Human creativity and meaning-making abilities, combined with quantum AI's ability to maintain coherent superpositions of multiple perspectives, simultaneously might generate insights that transform our understanding of consciousness, reality, and the relationship between mind and cosmos. This technological evolution occurs against the backdrop of quantum uncertainty that ensures the future remains genuinely unpredictable. Even perfect knowledge of current conditions cannot determine future outcomes when quantum randomness continuously injects novelty into physical processes. the universe maintains its capacity for surprise regardless of how sophisticated our predictive capabilities become. The development of quantum technologies doesn't eliminate uncertainty, but reveals new layers of mystery at every scale. Quantum computers exploit uncertainty as a computational resource using superposition and cannot access. Quantum sensors achieved entanglement to explore solution spaces that classical systems' precision limited only by fundamental physical constants, revealing phenomena that were previously undetectable. Quantum communication systems use the no-cloning theorem and measurement disturbance effects ably secure against any possible eavesdropping, to create information channels that are of same quantum properties that make perfect knowledge impossible also make perfect secrecy achievable, suggesting deep connections between uncertainty and privacy that have profound implications for information security in an increasingly connected world. Quantum biology continues to reveal that living systems exploit quantum effects in ways that seemed impossible just decades ago. Photosynthesis, enzyme catalysis, bird navigation, and possibly even consciousness itself depend on quantum coherence effects that persist in warm, noisy biological environments. Evolution appears to have discovered quantum technologies long before human physicists understood the principles involved. The emergence of quantum effects in biological systems suggests that the boundary between quantum and classical physics is far more fluid than previously imagined. Life might represent a natural form of quantum technology that maintains coherence through mechanisms we are only beginning to understand. Biological systems could serve as inspiration for new quantum technologies that operate efficiently in realistic environments rather than requiring extreme isolation from thermal noise. Medical applications of quantum technology could revolutionize healthcare by providing diagnostic tools that operate at the limits of physical precision. Quantum sensors could detect individual molecules or even single atomic processes within living cells, revealing disease mechanisms at their most fundamental levels. Quantum-enhanced imaging could visualize biological structures with resolution limited only by the uncertainty principle itself. Therapeutic applications might exploit quantum effects to target specific molecular processes with unprecedented precision. Quantum coherence in biological systems could be manipulated to enhance healing processes or correct genetic defects at the quantum level. The boundary between physics and medicine becomes increasingly blurred as quantum effects in biological systems are understood and potentially controlled. The philosophical implications of these developments, consciousness, and reality itself, if challenge our most basic assumptions about the nature of life-living systems, are quantum technologies that evolution discovered through billions of years of experimentation, then consciousness might be a natural quantum phenomenon rather than an emergent property of classical neural networks. This quantum view of life suggests that the hard problem of consciousness might have a natural resolution within quantum mechanics. Instead of explaining how subjective experience emerges from objective physical processes, we might need to understand how the quantum realm of pure possibility becomes actualized through conscious observation. Mind and matter become complementary aspects of quantum reality rather than fundamentally different substances that somehow interact. The implications extend to questions about free will, moral responsibility, and the meaning of human existence. If consciousness participates in quantum measurement processes that help actualize reality, then conscious beings become co-creators of the universe rather than passive observers of predetermined events. Every choice, every observation, every moment of awareness contributes to the ongoing creation of the world we inhabit. This participatory universe model suggests that the search for meaning might be misguided if it assumes meaning exists independently of conscious observers. Instead, meaning might be continuously created through the interaction between consciousness and cosmos, emerging from the quantum dialogue between mind and world that has been unfolding since the first moment of awareness arose in the universe. The uncertainty principle reveals that this dialogue has no predetermined endpoint. The quantum nature of reality ensures that new possibilities continuously emerge through the creative interaction between consciousness and physical processes. The universe remains eternally open to surprise, discovery, and transformation through the ongoing participation of conscious observers. This openness to novelty might be the most profound gift that quantum uncertainty provides. In a completely predictable universe, there would be no room for genuine creativity, growth, or evolution. The fundamental uncertainty built into quantum mechanics creates the space within which consciousness can emerge, develop, and contribute something genuinely new to the cosmic story. The universe becomes not a machine executing predetermined algorithms, but an improvisation where consciousness and cosmos collaborate in creating something that neither could achieve alone. Each moment of awareness participates in this cosmic creativity, contributing unique perspectives that help actualize specific possibilities from the infinite quantum sea of potential realities. We find ourselves not as accidental byproducts of blind physical processes, but as essential participants in reality's ongoing project of self-discovery and self-creation. The uncertainty principle becomes our invitation to embrace mystery as a creative partner, contributing our own unique observations and choices to the universe's eternal exploration of its own infinite possibilities. In such a cosmos, ignorance is not a deficiency but a doorway, uncertainty is not an obstacle but an opportunity, and the limits of knowledge become the very conditions that make wisdom, beauty, and meaning possible. Heisenberg's discovery about measurement precision reveals itself as a key to understanding the deepest structures of existence limitation. Where becomes liberation and uncertainty becomes the foundation for everything conscious beings hold most precious about existence in a quantum universe. The quantum cosmos doesn't just contain consciousness, it is structured for consciousness, by consciousness, and through consciousness in ways that make the observer and the observed inseparable aspects of a single, ever-evolving reality. In revealing the limits of knowledge, quantum uncertainty paradoxically opens infinite possibilities for understanding, ensuring that the conversation between mind and world continues as long as conscious beings exist to participate in the eternal dance of possibility and actuality that we call existence. This eternal dance between consciousness and cosmos leads us to perhaps the most startling realization of all. Heisenberg's uncertainty principle doesn't just describe limits on what we can know about reality. It reveals that reality itself might be fundamentally unfinished, continuously created through an ongoing collaboration between quantum possibilities and conscious observation that extends far beyond the laboratory into every moment of your existence. Think about what you're doing right now as you process these words. Your brain isn't simply receiving information like a passive computer downloading data. Instead, you're actively constructing meaning through quantum processes that involve genuine uncertainty at every level. The neural networks firing in your head operate through electrochemical processes governed by quantum mechanics. The very thoughts you're thinking emerge from superpositions of synaptic states that collapse into specific patterns of understanding through mechanisms that remain mysterious even to neuroscientists. But here's what should completely reshape how you understand your own mind. The meaning you're extracting from these sentences doesn't exist independently in the words themselves. It emerges through the quantum interaction between the information patterns and your unique cognitive architecture shaped by every experience you've ever had. You're not discovering predetermined meanings, but participating in creating them through the very act of reading. This creative aspect of consciousness extends to memory itself. Every time you're not accessing, you recall a past event, a fixed recording stored in your brain like a video file on a computer. Instead, you're reconstructing that memory through quantum processes that necessarily alter it in subtle ways. Each act of remembering changes the memory being remembered, making your past as uncertain and malleable as yore has revealed that memory's future. Recent neuroscience research exists in something remarkably similar to quantum superposition states. Before you actively recall a specific memory, the neural networks associated with that experience maintain multiple potential versions simultaneously. The act of remembering collapses these superposed possibilities into a single reconstructed narrative, but that narrative incorporates influences from your current state of mind, recent experiences, and the specific context of the recall process. This means your personal history isn't a fixed record of events that happen to you, but an actively maintained construction that evolves through every moment of conscious reflection. You don't simply have memories, you continuously create them through quantum processes that blend past possibilities with present perspectives in ways that make the boundary between history and imagination increasingly fluid. The implications for personal identity are staggering. If your memories are quantum constructions rather than classical recordings, and if your thoughts emerge from superpositions that collapse through consciousness, then what exactly persists as you from moment to moment? The sense of being a continuous self might be more like a quantum field that maintains certain patterns while constantly fluctuating at deeper levels. This quantum view of identity helps explain phenomena that have puzzled philosophers and psychologists for centuries. Why do personality assessments often produce different results when administered at different times? In quantum superposition, because personality itself might exist with different aspects of your character becoming actualized depending on the specific contexts and questions that collapse your psychological state into measurable responses. The phenomenon of cognitive dissonance, where people hold contradictory beliefs simultaneously, makes perfect sense from a quantum perspective. Instead of being a logical failure, cognitive dissonance might represent the natural quantum state of consciousness, where multiple incompatible perspectives coexist in superposition until specific circumstances force you to collapse into a single consistent position. Even your deepest convictions and values might exist in quantum uncertainty until tested by specific moral dilemmas or life circumstances. You might believe you know how you would respond to ethical challenges, but quantum uncertainty ensures that your actual choices will emerge through the interaction between your superposed value systems and the particular details of real situations you encounter. This quantum nature of moral reasoning explains why ethical philosophy remains perpetually unresolved despite millennia of brilliant thinking. Moral questions don't have predetermined correct answers waiting to be discovered through logical analysis. Instead, ethical truths emerge through the quantum interaction between moral principles, situational contexts, and the conscious beings who must make actual decisions under uncertainty. The same uncertainty that governs quantum particles also governs the most intimate aspects of human relationships. When you try to understand someone you love, you discover that people exist in emotional and psychological superpositions that collapse into specific behaviors only through the act of interaction itself. The version of a person you experience depends fundamentally on how you observe them, what questions you ask, and the relationship context you create together. This doesn't mean that people are completely arbitrary or that relationships are purely subjective, but it does mean that authentic intimacy requires embracing uncertainty as a creative force rather than trying to eliminate it through complete knowledge. The most profound human connections emerge not from perfect understanding, but from the willingness to remain perpetually surprised by the people you think you know best. Love itself might be fundamentally quantum in nature, creating entanglement effects where the emotional states of partners become correlated across any distance. When someone you love experiences joy or pain, you often respond immediately, even without direct communication, suggesting connections that transcend classical information transfer. These emotional correlations might represent genuine quantum entanglement between consciousness systems that have become coupled through intimate interaction. The development of empathy and compassion could depend on quantum coherence effects that allow consciousness to temporarily transcend individual boundaries and experience reality from other perspectives. The most profound moments of human understanding might occur when the normal classical barriers between minds become temporarily transparent, allowing direct sharing of subjective experience through quantum channels. But quantum uncertainty also protects individual privacy and autonomy in ways that classical physics never could. The no-cloning theorem suggests that conscious states cannot be perfectly copied or transferred, ensuring that each person's inner experience remains irreducibly unique. Even with perfect brain scanning technology, the quantum aspects of consciousness would remain fundamentally private because any attempt to measure them would necessarily disturb the very phenomena to creativity and artistic expression. The being observed. This quantum privacy extends most innovative ideas, and breakthrough insights might emerge from quantum superpositions in neural networks that explore multiple conceptual possibilities simultaneously. The aha moment of creative discovery could represent the collapse of these superposed ideas into specific innovations that surprise even their creators. Artistic creation becomes a quantum measurement process where the artist doesn't simply express predetermined ideas, but participates in actualizing specific possibilities from a potential. Each brushstroke, were infinite space of creative choice, or musical phrase collapses aesthetic superpositions into definite expressions while simultaneously opening new possibilities for future creative exploration. The appreciation of art involves similar quantum processes where meaning emerges through the interaction between the artwork and the observer's consciousness. The same painting or poem can evoke completely different responses in different viewers, not because of subjective interpretation alone, but because of genuine quantum interactions between the information patterns in the artwork and the unique cognitive architectures of different observers. This quantum view of aesthetics explains why great art remains perpetually fresh and surprising, even after countless encounters. Each viewing collapses different aspects of the artwork's meaning potential, while leaving other possibilities unexplored, ensuring that masterpieces continue revealing new dimensions of significance across generations of observers. The implications extend to education and learning, where knowledge transfer becomes understood as quantum entanglement between minds rather than classical information transmission. The most effective teaching doesn't involve downloading facts into passive students, but creating conditions where genuine understanding can emerge through quantum interactions between new information and existing cognitive structures. Learning becomes a creative process where students don't simply absorb predetermined knowledge, but participate in generating understanding through the collapse of educational superpositions. The same lesson can produce radically different learning outcomes in different students because understanding itself emerges through quantum processes that depend on the unique perspectives and backgrounds each learner brings to the interaction. Assessment and evaluation face fundamental quantum measurement problems where the act of testing necessarily changes what's being measured. Students' knowledge exists in superposition until collapsed by specific exam questions that may reveal only limited aspects of their actual understanding. The measurement process becomes entangled with the learning process in ways that make objective evaluation increasingly problematic. Personalized learning systems powered by artificial intelligence attempt to navigate these quantum uncertainties by continuously adapting to individual student responses. But these systems create feedback loops where the algorithm's attempts to measure learning inevitably alter the learning process itself, creating new forms of educational uncertainty that require quantum-aware pedagogical approaches. The democratization of knowledge through digital technologies reveals quantum effects at social scales where information doesn't simply spread through populations, but evolves through collective interaction. Ideas exist in cultural superposition until collapsed by specific social contexts that determine which interpretations become widely accepted. The same information can lead to completely different cultural outcomes depending on the specific networks and communities through which it propagates. Social media algorithms create quantum measurement effects where the act of observing user behavior changes the very behaviors being observed. Recommendation systems dawn through feedback loops that user preferences but participate in creating them that simply entangle individual choices with collective patterns in ways that make personal autonomy and increasingly difficult to separate. The phenomenon of social influence of viral content demonstrates quantum-like properties where small variations in timing, context, or presentation can determine whether ideas reach millions of people. or disappear into digital obscurity. The same message can succeed brilliantly or fail completely depending on quantum fluctuations in network dynamics that remain fundamentally unpredictable despite sophisticated analytical tools. Political movements exhibit similar quantum behaviors, where individual opinions become entangled in ways that create emergent collective consciousness. Public opinion doesn't simply aggregate individual preferences, but emerges through quantum-like interactions between personal beliefs and social contexts that can produce sudden phase transitions in popular sentiment. The polling paradox reveals quantum measurement problems in democratic systems where the act of measuring public opinion participates in creating the very opinions being measured. Election predictions become entangled with election outcomes through feedback effects that make the boundary between objective analysis and political influence increasingly meaningless. Revolutionary social changes often occur through quantum-like processes where gradual accumulation of individual dissatisfaction suddenly crystallizes into collective action that transforms entire societies. These social phase transitions cannot be predicted precisely because they depend on countless effects in ways that mirror quantum field dynamics. Economic systems demonstrate small interactions that amplify through network quantum uncertainty principles, where market behavior emerges from the interaction between individual decisions and collective dynamics in ways that make perfect prediction impossible even in principle. Financial markets exist in superposition between multiple potential futures until collapsed by specific events that actualize particular economic realities from the quantum space of possibilities. We began this journey with Heisenberg staring at an electron in a German laboratory, trying to make a simple measurement. What we discovered is that this young physicist wasn't just uncovering a technical limitation of scientific instruments. He was revealing the most profound truth about existence itself. Reality refuses to be pinned down because uncertainty isn't a bug in the system. It's the feature that makes everything possible. From the quantum foam bubbling in empty space to the thoughts forming in your mind right now, uncertainty weaves through every level of existence. Your memories, your relationships, your creative insights, even your sense of self all emerge from quantum processes where possibility becomes actuality through the mysterious dance between consciousness and cosmos. The uncertainty principle shows us that we're not passive observers of a predetermined universe. We're active participants in reality's ongoing creation, temporary patterns of awareness that emerge from quantum possibility and contribute something genuinely unique to the cosmic story. In revealing the limits of knowledge, Heisenberg paradoxically opened infinite possibilities for discovery, ensuring that mystery remains the eternal companion of truth in our endless exploration of existence itself.